This is question 1 on homework 4. It asks us to imagine a rope and pulley system here, where the pulley is very light. We're asked to find the tension in the string, the acceleration of the masses first. So let's do that. We've already got our cartoon drawn, so the first thing to do is to draw the force diagrams. It'll always be the case. So for this object, I've got a normal force going upward, gravity going downward, and then the tension in the string going to the right. That's for M1. And for M2, let's see, we've got its weight going downward and tension going upward. Notice that I've used M1 and M2 rather than big M and little m, just because it's clearer. This homework problem, I got the diagram from an old textbook, and that diagram had big M and little m, but M1 and M2 is much clearer. The two tension forces are the same because it is a long rope. Now, the next thing to do is to construct Newton's laws. I'm going to have 3 equations, one for x and y in this, and one for y for that. We need to draw some coordinate systems. So you can pick any coordinate system you like. I'm going to pick the conventional one, like this, for both objects, although there's a reason you might not want to do that, which we'll see in a minute. So for M1, in the x direction, I can just read this off of my diagrams. So I have t equals m1a1x. For m1 in the y direction, let's see, in the y direction I have the normal force and m1g. Normal force minus m1g equals m1a1y. And then, for the hanging object, it's only got stuff in the y direction. We have t minus m2g equals m2a2y. Now, a couple things. Notice that I've used different acceleration variables for everything. Whenever you have multiple objects, a problem with multiple objects, the safe thing to do is to use different acceleration variables for everything and think about their relationship later. So here, in this case, I know a1y is 0. So all that is 0. This is 0 because this doesn't move up or down. And that means that in this equation just tells me, if this is 0, that the normal force equals m1g. That's true, but it's not terribly useful. So this is kind of boring. I'm just actually going to erase this equation. I found out that the normal force on this is equal to its weight, but it doesn't really matter for anything, because it doesn't have any variables in common with the other equations. It doesn't relate to what I want to know. So I've got these two equations, but I've got 3 unknowns. I don't know the tension, and I have 2 different unknown accelerations. So at this point, we have a constraint on those accelerations. We know that this object is going to go that way, and this object is going to go down. So however fast this moves to the right, this must move down at the same rate. But you might say, oh, well, a1x is equal to a2y. So I could say, potentially, a1x equals maybe a2y. But they're not equal. Their magnitudes are equal, but really, this one goes to the right, and this one goes down. If this moves in plus x, this one will move in minus y. So that means the relationship here is really that a1x equals minus a2y. Or you can put the minus sign on the other side. This is not about which one is moving up and which one is moving down. It's about the idea that they have equal magnitudes but the opposite sign. And now we can actually do the algebra. So I've got these two equations. I'm going to solve this one for t. Comes up here. So, well, that's already done. So t equals m1 a1x. But a1x is minus a2y. So I'm going to substitute that in here just to get rid of the other variable. This is equal to minus m1, I'll write it more clearly, equals minus m1 a2y, where this thing, this equality, has been used for that substitution. Now we substitute this into this equation down here. So we're going to take this equation, we're going to bring it up here, and I'm going to substitute in that value for the tension. So I have minus m1 a2y, and then I copy the rest of the equation, minus m2g equals m2 a2y. So now let's solve for a2y. Just bring this term over to the other side. I get minus m2g equals m1 plus m2 times a2y. So that means that a2y equals minus m2g over m1 plus m2. That's a smudge, not a minus sign. So I found a2y. And if we want a1x, well, that's just this without the minus sign. a1x equals m2g over m1 plus m2. So now I've got those results. Now I need to go back and find the tension. I know the tension is just a1x multiplied by m1. So we'll put this here. T equals m1 a1x. So T is just this times m1, which is m1 m2g over m1 plus m2. So that's the result for part A. So I've got my results for part A. What's the process that I did? I drew force diagrams. I converted them to expressions of Newton's laws. I thought about my constraint, that the two accelerations are equal in magnitude but opposite in sign. And then I did my algebra to solve for what I want. So now I'm going to make all of this go away. And we're going to do parts B and C. So part B says, what is t in the limit where m1 is much bigger than m2? Well, if m1 is much bigger than m2, think of this is a brick and that's a feather. And my computer went to sleep. Give me just a minute. Yep, it's still recording. If m1 is much bigger than m2, this is a brick, this is a feather, and if I attach a feather to the brick, nothing's really going to move. And that means that m2 is just suspended by a string, and the tension in that string, it's not moving, ought to be equal to its weight. So we expect the tension in that limit to be m2g. So let's take our formula here for the tension. T is m1 m2g over m1 plus m2. But in this limit, where m1 is way bigger than m2, then this doesn't matter. Right? Adding a small thing to a large thing is basically just the same as the large thing. So that's m1 m2g over m1. I can cancel the m1s, and I get a tension of m2g. So what I see is if I hang a feather from a brick, then the tension in the string is just the weight of the feather, which is what I expect if m1 is way bigger than m2. Okay? So part C asks us to find the acceleration in the limit where m2 is much bigger than m1. So what happens here? In this case, I've got m2 is a brick, m1 is a feather, and if I attach a brick to a feather, it's just going to fall. The feather shouldn't do anything. So we expect the acceleration to basically be free fall. A brick tied to a feather is just going to fall freely. So our formula for a1x is m2g over m1 plus m2. But if m2 is way bigger than m1, then this is irrelevant. Adding the mass of a feather to the mass of a brick is just the mass of a brick. So that's approximately equal to m2g over m2, which is just g. So we got what we expected. These last two parts are actually really, really critical in engineering, and in physics, and in all sciences. It turns out that the idea of limits and approximations, limiting cases, is really, really valuable because it lets us take hard math and turn it into easy math. This is all over the place, in engineering, in physics, in chemistry, and in every science. And this is kind of at the intersection of the mathematical idea of limits, which I've applied here, to the physical reality of limits, that tying a feather to a brick doesn't really change how the brick falls. And if I do it the other way around, then a feather tied to a brick is just not going to move. So that's question one.